Okay, this is a quick video on geometrical problems with three-dimensional vectors, and we're going to start by looking at how to find the area of a triangle given kind of coordinates or two vectors perhaps, and you can obviously use that to then calculate areas of parallelograms or any other polyhedra in 2 dimensions, or so in two-dimensional shape in a three-dimensional space. And then we're going to have a look at a geometrical proof, which is very similar to the year 1 proofs, but with the 3D vectors kicking around. But the process really isn't much different. Okay, so the area of a triangle. Well, first of all, let's just consider this vector here. This vector has length, let's say, the magnitude of A, and that's the magnitude of B. I know it's not, that's what you're used to for notation, but let's just say this vector here is the vector A, and this vector here is the vector B. Then the length of that is magnitude A, length of that is magnitude B. We can calculate this vector. It doesn't matter which way you go, but that vector is going to be B minus A, or A minus B if you're going the other way. But if you find the magnitude of that, that'll give you the length of it. And you've got the length of all 3 sides. We can then use the cosine rule to calculate theta, and then you can use the area of a triangle is a half AB sine C to find the area of the triangle. That's the process that we're looking to go down. Okay, that's the route that we're looking to follow. Okay. Let's have a look at an example. So I've got a triangle here. It's got 3 coordinates for its vertices, and notice that all 3 of those vertices are in 3-dimensional space, as you'd expect for this example. And we're going to do exactly what I just said. We're going to calculate the magnitude of all of those 3 lengths, and then we're going to use the cosine rule to find one of the angles, and then we're going to use the area of a triangle formula to find the area of that triangle. Okay, so the length. As mentioned on my previous video, we can use 3-dimensional Pythagoras. So this length here, I'll draw this one out for the first one so you can see what I'm doing. Let's call this one L1. By Pythagoras, L1 is going to equal the square root of the difference in x squared. Well, we've gone from -1 to 0, so that's 1 squared. Plus the difference in y squared, where we've gone from 2 to 5, so that's 3 squared. Plus the difference in z squared, where we've gone from 3 to 2, which is a difference of -1 squared. You don't need the negative, but I'll just put it in there just so you can see what I'm doing. So that's going to be the square root of 11. Okay, so that's exactly what I'm going to do for the other 2. This length here is the square root of 11. Okay. All right, this length here. So square root of, difference in the x is 3, so that's 3 squared. Difference in the y is 3, so plus 3 squared. And the difference in the z is -3, so again, plus another 3 squared. And that gives me 3 root 3. Or root 27, if you like. And then the difference between the x's here, we're going to have 2 squared. Plus the difference in the y's, which is 0. Plus the difference in the z's, which is 2. So we end up with 2 root 2. Okay. So those are the 3 lengths of my triangle. Choose an angle, doesn't matter which one. I'm going to choose this one. And using the cosine rule, I know that theta is going to equal arc cos of the 2 adjacent lengths next to it, squared and summed. So that's going to be the square root of 11 squared, plus 3 root 3 squared. Subtract the opposite length, which is 2 root 2 squared, so -8. And that's all divided by 2 times the product of the adjacent lengths. So root 11 times 3 root 3. If I dump all that into my calculator, I should hopefully get my angle out. So inverse cosine of 11 plus 27 minus 8 divided by the square root of 2 root 11, oops, no square root there, 2 root 11 times 3 root 3. And that gives me 29.496 degrees. You can work in radians, it's not a problem because this is a intermediary calculation for what you're trying to do, as long as you're consistent with your units. The area then, well, the area of a triangle is going to half AB sine C, so it's going to be half times root 11 times 3 root 3 times the sine of the angle in between them. okay, which I've just calculated here. So plug all that in, 0.5 times the square root of 11 times 3 root 3 times sine of my answer. And that gives me 4.24 to 2 decimal places. Okay, and that's my answer. That's the area of that triangle in three-dimensional space. And if you choose any 3 points in three-dimensional space, they will form a triangle unless they are collinear, in which case the area of the triangle is 0 because all 3 points lie on a straight line. So you can do that really for any points. Okay. All right. The other application that I wanted to look at was the geometrical proof. This is one of the trickier questions that you would perhaps come across. I've got a parallelepiped. Now, a parallelepiped is the name of a three-dimensional shape where each of its faces are parallelograms, and moreover, the opposite faces are exactly the same parallelogram. Okay, so this shape over here is exactly the same shape as this one. The one facing you is exactly the same shape as the one at the back, and the one on top is exactly the same shape as the one on the bottom. They are all parallelograms. Okay, so that's what a parallelepiped is. You can define a parallelepiped with 3 vectors. I've called this one A, B, and C, and more conventionally, A goes from O to A, B goes from O to B, and C goes from O to C. Okay, that's kind of the convention we work with in maths. Then we've also got other points, D, E, F, and G are other vertices of the parallelepiped. Okay, so we've got some definitions here. We've got M, we're told is the midpoint of EF. So M is halfway from E to F. And N is the midpoint of EM. So N is halfway from E to M. So if you like, it's a quarter of the way from E to F. And we know that because M is halfway from E to F. And N is half of that. So it's a quarter of the way. CN, so that's the line going from this vertex to that point. And OM, so that goes from the origin to the midpoint over here, intersect at the point X. So I've labelled X. I know it looks like X is on the line AD, but it's not. It's behind it. It's actually inside the parallelepiped. And we are asked to find the ratio OX to XM. Okay. So just like in 2 dimensions, we need to approach the point X from 2 different directions to answer this. So first direction I'm going to consider is that to get from O to X, that is just some proportion of the vector from O to M. And that I can state that because X is on the line OM. In other words, OX is parallel to OM. Okay. I'm expecting lambda to be a number that's less than 1, but bigger than 0. And that's just because X doesn't quite make it all the way to M. So you'd expect the vector OX to be less than the vector OM. Okay. So I'm expecting a number between 0 and 1. That's important when we come to check our answer later. Okay, well, what is OM? Well, I really want OM in terms of my A, B's and C's. So I can add A, I can add B, and then I can add half of C. So that's A plus B plus half of C. Okay, so that's one way to get from O to X. And the route I've taken, I'm just going to highlight it in green. Gone that way, that's A, plus that way, that's E, plus that way to get to M. So the route I've taken is this line here. All right, we can do the same thing, but now approaching X from different directions. So either approach it from the point N or approaching it from the point C. So OX, I'm going to say is OC plus CX. So O to C plus C to X. O to C, I'll leave that alone for a minute. I'll come back to that. Plus C to X, well, that's going to be some constant, not lambda, but mu, okay, another constant, of C to N, for exactly the same reason that OX was a constant times O to M. Okay. And that's going to be OC plus mu times c to n. Well, how do I get from c to n? Well, we can either go this way, up, and then that way, or we can consider going this way, that way, that way, that way. So it doesn't really matter how you get there, as long as you can express from c to n in terms of a, b, and c. So we can actually get there using 3 arcs. So I can go that way, I can go up, and then I can go across, and that will approach this point here then from that direction. And I've also used OC. Okay. So to get from C to N, I've gone back that way, so that's plus a B. I've gone up, G to F, that's the same as A. And then I've gone 3/4 of the way that way, which is minus 3/4 C. Okay. And now OC is just C. So we can actually write O to X as mu A plus mu B plus 1 minus 3/4 mu C. Okay, so there's 1 C from there, 1 C, minus 3/4 mu C from here. Okay, so I've now got O to X in terms of A, B, and C, and O to X in terms of A, B, and C. So I can equate the coefficients. So I've approached X from 2 different directions, but they're both the vector O to X. So therefore they both must be the same. And they must be the same whatever A, B, and C are. So I can equate these two. So I can say that lambda A plus lambda B plus a half lambda C is identical to mu A plus mu B plus 1 minus 3/4 mu C. Okay, that has to be true for whatever A, B, and C are. Okay. A, B, and C aren't defined explicitly in this question, and I've expressed O to X in terms of those A, B's, and C's. So however I approach X from O, they must be identical. So these two must be identical, which means I can equate the coefficients of A, which means I get lambda on the left is equal to mu on the right. I can equate the coefficients of B, which means lambda on the left is equal to mu on the right. Okay, that's actually no new information because those two are the same. And the point C, so the vector C, a half lambda, that must equal 1 minus 3/4 mu. Okay, and what I've got here is a pair of simultaneous equations, if I ignore the top one, in lambda and mu. So I can solve these. So if I go into equation solver, simultaneous equation with 2 unknowns, I'm going to say X is lambda and Y is mu. So lambda minus mu is 0. That's the lambda equals mu one. And then I also have this one. I'm going to times it by 4. So I'm going to get 2 lambda plus 3 mu. Okay, times it by 4 and then add 3 mu equals 4. And that gives me that lambda equals mu, which we know from the first two, equals 4/5. Okay, equals 4/5. So what does that tell us in terms of the original problem? Well, this says that lambda is 4/5. So from O to X, that is 4/5 of the way from O to M, because OX is lambda times OM. So that means O to X is 4/5 of O to M. Therefore, OX is 4/5 and XM is the remaining 1/5. And I've done that because the question is asking for the ratio of OX to XM. So if OX is 4/5 and XM is 1/5, then the ratio OX to XM is equal to 4/5 to 1/5, or if you like, 4 to 1. And that's the answer. Okay. So it's exactly the same principle as first year geometrical problems. We approach the points from 2 different directions and we equate coefficients, evaluating the scalar values, and then that allows us to produce a ratio. Okay, that's typically kind of 5 marks-ish. All right. That's it for applications. There is one more video to come, which is just a little bit on mechanics with three-dimensional vectors, but again, nothing too taxing in that. Thank you for watching.